Hello everyone, welcome back to my channel. My name is Dr. Yogita Bish and this is the 6th video of my video series Chemical Bonding. So till now I have explained everything related to the Lewis structure, the postulates, the limitations, how to draw step by step draw the structure, how to remember few important points. All these things I have already explained. Now moving forward, before we move forward to the next approach, it is very important to understand few topics. For example, resonance, dipole moment, Fisson's rules, where the ionic bond try to show some covalency. All these topics are very important to understand the other approaches. So in the next few videos I explain these topics. So in today's video I'll explain the resonance. And this resonance we are going to study again in organic in detail, but right now I'll just give you the idea about the resonance, and we will also study about the resonance structure of the carbonate, carbon dioxide and the ozone molecule. Okay, so let's just start. So I'll start with an example of the carbonate ion, and we have already explained how to draw the Lewis structure of the carbonate ion, but sometimes this happens that one particular structure is not good enough to explain all the property or proper structure of that particular molecule. That's why we have to draw more than one structures, and there the term resonance come into picture. But before we go into that, first we need to draw the Lewis structure of the carbonate ion. So let's just start with that. So try to recall the concept, and if you can't remember that, you can just re-watch my videos. I'll provide the link for the same. So I'll quickly do that. First step for this is to calculate the total valence electron. So I'll do the sum. So for the carbon it is 4, for oxygen it is 6, multiplied by 3, because -2 sign is there, we have to add 2. So this will make it 24. Then we have to find the lone pair electrons. We can do that by subtracting the bond pair electron multiplied by 2 from the total valence electron. So how to find that out? First we need to find the central atom and assign the other atom around it with a single bond. Okay, 3 oxygens are there, so we are going to attach it with a single bond via single bond to the central atom. Alright, so we have 1, 2, 3, 3 single bonds. So we are going to subtract 3 into 2. These are our bond pair electron. Whatever the single bonds are there, multiplied by 2. So this will give us 18. Right? So we have the lone pair electron. Now we are going to arrange this lone pair electron around these atoms. Okay, so this will give you 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we have total 6 lone pair of electron, but this is not the right structure. After assigning all the lone pair of electron, we have to check whether the octet is complete or not. And it is very important to check the octet of the central atom. Although we have to check the octet of other atoms also, but central atom can have more than 8 electrons as well, but it must, in any condition, must have at least 8 electron. Okay, so let's just check. So in case of oxygen it is 1, 2, 3, 4, 5, 6, 7, 8, right? Single bond is considered 2 bond pair electrons, so total 8 electrons are there. Same goes for this oxygen and same goes for the third oxygen as well. What about carbon? Carbon has 4 valency, right? But we have only 3 bonds. So in that case, what we have to do, we have to convert one of the lone pair of electron, use it for the double bond. Okay, we have to use it for the double bond. So the actual structure, which is a right Lewis structure, is something like this. We are going to join it with the double bond, and whatever left will be the lone pair. Okay, and the other oxygen would remain unaffected. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is first structure of the carbonate as per the rule. Okay, we can also assign the formal charges here. So in case of formal charges, I'm not going to repeat the formula for the same. You can just re-watch the videos, but here I'm assigning the number 1, 2, 3 and oxygen as fourth. Okay, so in this case, first oxygen and second oxygen are same. What are the formal charges on these oxygen? So that is given by valence electron. In that case, this case, oxygen has 6 minus whatever the lone pair of electrons are there, 1, 2, 3, 4, 5, 6, minus whatever the bond electrons are there, that is 2, divided by 2. So it has minus 1 charge. So both this oxygen as well as this oxygen, they are exactly same, right? So they both have the negative charge. Similarly, the third oxygen, we can calculate for this as well. So it is oxygen, so 6 minus lone pair 1, 2, 3, 4, minus how many bond pairs are there? 2 plus 2, 4, right? 4, whatever the bond pair electrons are there, divide by 2. So it's 0. So it doesn't have any charge. So when a particular atom doesn't have any charge, we don't show it, right? And then fourth atom, that is carbon. So in case of carbon, 4 electrons are there in the valence shell. So 4, so it is 4 minus, there are no lone pair, minus 0, minus how many bonds are there? 1, 2, 3, 4. 4 into 2, 8. 8 divided by 2. So this is 0. So this carbon also doesn't have any charge. So if I have to rewrite this, just a second. So if I have to rewrite this, I can rewrite this structure 1 as carbon, double bond oxygen, 2 lone pair, this oxygen, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This has negative charge, this has negative charge. So this is first structure. Now, what is so special about this oxygen? This could be this oxygen and other oxygen also, and that actually what happened, this pi electron keep on moving. Okay, so what is going to happen, this electron, lone pair of electron, can actually form a double bond, and this pi electron can move back to this oxygen. That is also a possibility. Okay, so in that case, we'll have similar structure, another structure which is exactly same in the energy, in terms of positioning of atom, everything same. Okay, so we can also show it like this, 1, 2, 3, 4, 5, 6 with a negative charge, and here we will have double bond, 1, 2, 3, 4 without any charge, and then this oxygen, 1, 2, 3, 4, 5, 6 with a negative charge, right? Now what can happen, the third oxygen is also same, right? So these pi electron can form double bond, and this double bond can go back. Then we will have another structure, this is structure number 2. So we can also have another structure which will look like something like this, 1, 2, 3, 4 minus, and this oxygen 1, 2, 3, 4, 5, 6 minus, and here double bond oxygen 1, 2, 3, 4. Okay, this is the third structure. Now all these 3 structures, they are exactly same. That is why I am representing them like this. Okay, double arrow. Okay, so these structures, they are exactly same, and these structures are called as canonical structures. What does it mean? It means it shows the possibility that the atom, the molecule, carbonate molecule can exist like this. Okay, but this is not a real structure. Actually, experimentally when it was found that none of the bond have a pure double bond character or the single bond character. Rather, we have something like this. We have carbon, oxygen, 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 and double bond actually appear like this, dotted, and the negative 2 charge is not residing on one of the single oxygen or the other single oxygen, rather it is residing on the complete molecule, and this is how we represent the actual structure of the carbonate ion. This is called as hybrid structure. Okay, these are also called canonical structure or resonance structure, and this actual structure which was experimentally found is called as hybrid structure. Okay, so from this the concept of the resonance come into picture. When one single Lewis structure is not good enough to represent the structure of a molecule, we can represent it with the multiple structure, then that concept is known as resonance hybrid. So if you go by the exact definition, it says, according to the concept of the resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with a similar energy, position of the nuclei, bonding and non-bonding pair of electrons are taken as the canonical structure of the hybrid, which describe the molecule. Okay. So whatever I have explained, this is exactly talking about the same, that a single Lewis structure cannot explain it, then we have to show it by multiple structures, but these structures are not the real structure. The real structure lies something in between, and which was shown or proven experimentally. Okay. So yeah, if this text is not visible, let me just show it. Okay, so I hope this is clear. Now let's just try with some other example. Let's move to the carbon dioxide and then ozone molecule. Okay. Alright, so we'll start with the, let's say, carbon dioxide. Okay, so again we can calculate the total valence electron. In case of carbon dioxide, it is 4 plus 12, 16. Lone pair of electrons. How do we represent the carbon dioxide molecule? First we will join it with a single bond. So total 2 single bonds are there. So the lone pair of electron would be 16 minus 4, that is 12. So we have to arrange 12 electrons around these atoms, oxygen atoms, right? You can calculate the formal charges also. Okay, and you will see that these. So now we will check the octet rule. So here we have the complete octet for the oxygen. Here also we have a complete octet for the oxygen. But what about the carbon? Carbon has only 2 bonding here, right? So what is going to happen? There are multiple possibility. One, these lone pair electron can come here, and this lone pair electron can come here, and we can have something like this. Carbon double bond oxygen, carbon double bond oxygen. Okay, this is the first structure, and I hope you can calculate the formal charges on each atom. So let's just do the calculation quickly. The formal charges on first, second and third. So in this particular case, first and second are same. So oxygen, the charges on the oxygen would be, it will be 6 minus 0 minus 2 plus 2, 4 divided by, sorry, we have not put in the lone pair of electrons. So it will be 6 minus 4 minus 4 divided by 2. It will be 0. And in case of third carbon, so it will be 4 minus 0 minus 8 divided by 2, that is 0. So each of these atom doesn't have any charge. So this is one of the expected structure. Now there are other structures also. Now instead of taking the lone pair from both the oxygen, it can take 2 bonds from the same oxygen. So if that happen, then what we can show is, this will have same charges, but this will form triple bond with the oxygen. So it will have 1, 2, and this will have 6 electron. You can calculate the charges as well. So if you calculate the charges, you will realize this oxygen has a negative charge, whereas this oxygen has a plus charge, and carbon doesn't have any charge. If you want, we can calculate it also. Formal charges in this particular case, this is first oxygen. Let's just write 1, 2, 3. This is second oxygen, and this is second carbon, and this is third oxygen. So in case of first oxygen, the formal charge would be 6 minus 2 by 2. This is minus 1. In case of carbon, it will be 4 minus 0 minus 8 by 2. Again 0. What about the third atom? The third oxygen, it will be formal charge in this case would be 6 minus 2 minus 6 by 2, right? So this will be plus 1. So this will have plus charge, this will have 0 charge, this will have negative charge. Okay. And similarly, we can also have third structure, which will look like this. Carbon, instead of making triple bond with this oxygen, it can also make triple bond with the other oxygen. We can have something like that, right? 1, 2, 3, 4, 5, 6, and here only 1, 2, and it can have plus charge. This is the third structure, right? So this was the first structure, this was the second structure, this was the third structure, right? So these structures, they all have the possibilities, they all have the same energy. So these three structures are the canonical or resonance structure of carbon dioxide. Okay, I hope this is clear. Now we don't have the exact hybrid structure here, right? So hybrid structure would be something in between these three structures, which is something which we are going to find experimentally and then assign the charges overall on all three atoms. Okay, so that will be our hybrid structure. Let's just quickly do it for the last atom, that is the the ozone molecule. Now the ozone molecule, I am not going to do the calculation for this, you can do it later on, and if you don't understand this, you can just write it in the comment box. I'll provide the complete description for the same. So the ozone molecule, it look like something like this. Okay, so it has a double bond with one of the oxygen and the single bond with the another oxygen, and this is how we represent it. Minus charge, 1, 2, 3, 4, 0 charge, and this will have 1, 2 and a plus charge. Okay, you can do the calculations here, and always remember, you need not to calculate the formal charge again and again. Always remember, when oxygen has 6 lone pair and a single bond, then it will always have a negative charge. When it has 2 lone pair and a double bond, it has a 0 charge, and when it has 3 bond pair, 3 bonding and 1 lone pair, then it has a plus charge. So just after doing multiple examples, you will always remember that. Okay, so this is one of the way of representation. Okay, now as you can see, this is a double bond, right? So experimentally, the double bond, it is actually the double bond between oxygen and oxygen has a bond length of 121 picometer, whereas a single bond has a bond length of 148 picometer. Okay, but experimentally it was found that none of the bond length was 121 or 148. In fact, every bond length was 128. That is a mixture of that is something in between the double bond and the single bond. Okay, first let's just draw the canonical structure or the resonance structure for the same. So we can also show double bond on the right hand side rather than the left hand side. So in that case we can represent like this: 1 2 3 4 5 6 minus charge, and here a plus charge. These two are the canonical structure, but both are wrong. Wrong in the sense they do not exist. It's not a mixture. It's not like half of the time it will exist as this structure, and half of the point it will exist as this structure. No, these are not the real structure. These are just the canonical structure or the theoretical structure. Actually, the real structure is hybrid of this. Hybrid of this means we will have something like this: a double bond, the pi electron, which are delocalized like this. Okay, and the negative charge will not reside on one of the oxygen atom, rather it will reside on the two oxygen atom, half this side and the half the other side. And how do we get to know about this? By some experimental data and correlating with the theory. Okay, so I hope this is clear. Let's just quickly go through some of the very important point that you must remember. First is resonance structure stabilizes the molecule. So if a molecule has multiple, see here in case of ozone only two canonical structure were possible, right? In case of carbon dioxide 3 canonical structure were possible, right? In case of carbonate ion 3 canonical structures were possible, and there are chances that in other molecule more than 3 are possible, right? So whatever the number of higher the number of the resonance structure or the canonical structure, better will be the stability of the molecule. Why? Because as this is the movement of the pi electron, as it move from as there is a movement of the pi electron to convert one form into the other form, they are going to release energy, and whenever there is a release of energy, there will be overall decrease in energy, and if a molecule has a lesser energy, it is more stable. This is the basic rule of the chemistry. Any system want to lose energy to gain the stability. So resonance is something that is favoring the stability. Okay, then second point, the canonical structure or the resonance structure, they do not exist in real. That can be a multiple choice question also, like it do not exist in real, though we draw that, but experimentally it is not proven that it exists like this. Okay, so molecule has only one single structure, which is the hybrid structure. Only the hybrid structure is the real structure. Okay, in this case this one, and in carbonate case I have already shown you, this is the actual structure. Okay, so I hope everything is clear. So I'll see you in the next video with the dipole moment. Okay, thank you.